All right, so where we're headed today. Yesterday, we'd gotten as far as laying out the structure of the renal corpuscle. We placed the glomerular capillary inside or within the boundary of Bowman's capsule. And we began to talk about the fluid movement from the blood vascular compartment, that is the glomerular capillary, into the renal compartment, in that case, Bowman's capsule. And we'd started to describe the pressures that were moving the fluid from one compartment to the next. The two pressures we talked about were the pressure called the hydrostatic pressure, which was the pressure that's generated against the wall. It's the same hydrostatic pressure that we talked about earlier in generating lymph. But we also said, just as we talked about the generation of lymph, that once we squeezed the water out of that capillary, we left protein behind. And because of the protein that remained behind, that generated an osmotic force that drew the fluid back in again. We're going to add one more force on top of that. There's going to be a pressure called the hydrostatic pressure of Bowman's capsule. You can think about the Bowman's capsule as being a closed environment sealed off around that glomerular capillary. And as you put fluid into that sealed off environment, it begins to swell, almost as though you were filling a balloon with water. That's going to generate a hydrostatic pressure. So we're going to find that there are two pressures moving the fluid from Bowman's capsule back into the glomerular capillary. One is the osmotic pressure and the other is the hydrostatic pressure of Bowman's capsule. But when you add those two together, those numbers come to about 45 millimeters of mercury. And you remember that the hydrostatic pressure on the wall of the glomerular capillary is like 55 millimeters of mercury. So that means we have a net pressure going from the glomerular capillary into Bowman's capsule. Whenever you get a pressure differential, unless you have an enormous resistance, we have a flow. So that now dictates a flow of fluid from the renal capillary, from the glomerulus, from the blood vascular compartment into the renal compartment. And if you look at the numbers there, the total movement of fluid from the blood vascular compartment into the renal compartment is in the neighborhood of 125 mils a minute. Now, not each individual nephron, not each individual Bowman's capsule receives that amount of fluid. You have to remember that there are roughly 500,000 nephrons in each kidney. So it's a millionth of each one of those for each one of the nephrons. But when you add them all together, we get a sizable movement of fluid. If you just take those numbers, say for an hour, imagine sitting in front of the TV for an hour while your kidneys are doing their job, you'll recognize that you'll move something like 5.7 liters of fluid from the blood vascular compartment into your kidney, which would then be in your bladder. Well, you know full well you don't put 6 liters of fluid into your bladder. So there has to be some story here where we begin to reabsorb this water. And one of the major ideas we're going to talk about today is this idea of reabsorption in the proximal convoluted tubule. We're going to see that once we've moved fluid into Bowman's capsule, that fluid largely drains into the next step that we drew yesterday of the nephron. And that next step is going to be the proximal convoluted tubule. Within the proximal convoluted tubule, we reabsorb something like 60% of the sodium and 60% of the water that we forced out of the blood vascular compartment into Bowman's capsule. That reabsorption occurs in the proximal convoluted tubule, and we'll talk about how that gets done. But there's another really important aspect of reabsorption in the proximal convoluted tubule that we need to think about. We find that 100%, if things are running properly and things are normal, 100% of the glucose that was forced out of the blood from the glomerulus and into Bowman's capsule, 100% of the glucose and 100% of the amino acids are reabsorbed in the proximal convoluted tubule and put back into the blood. We're going to see that most of the sodium and chloride and water are moving in something known as a paracellular route. They're moving around the cells. We're going to really contradict much of what we said about tight junctions earlier in the course. We're going to see now that tight junctions provide labyrinthine pathways through which ions and water can move. but we're going to move water and ions around the epithelial cells of the proximal convoluted tubule and into the extracellular space and then back into the blood vascular compartment. In contrast, we're going to move the glucose and amino acids in something known as a transcellular route. So the glucose and amino acids are going to move across the apical membrane of the epithelial cells into the cytoplasm and then across the basilar membrane and back into the blood. And we'll talk about how that gets done. Then the return is going to be into a structure known as the peritubular capillary. Now, as we draw this, recognize that there's continuity of these tubes, that there is an afferent arteriole feeding blood into the glomerular capillary. The glomerular capillary then has that blood drained into the efferent arteriole, which is carrying blood away from the glomerulus. But now that efferent arteriole forms another structure, form another tube called the peritubular capillary. And this peritubular capillary is going to snake around the proximal convoluted tubule. And we're now going to see then we're going to move molecules across the epithelium of the proximal convoluted tubule into the extracellular space and back across the endothelial cells of the peritubular capillaries to put back particularly glucose and amino acids and a good bit of sodium and water back into the blood vascular compartment. Then what we'll do is we'll redraw what we had on the board yesterday in trying to orient and organize the nephron. We're going to define the nephron as the structural and functional unit of the kidney. That may sound familiar to you. It sounds an awful lot like the neuron doctrine, where the neuron was the structural and functional unit of the nervous system. But in that case, it was an individual cell. In this case, the fundamental unit is a multicellular structure. It's a multicellular epithelial structure called the nephron. And the type of nephron we're going to talk about is one known as the juxtamedullary nephron. It's going to extend from the cortex, where we have Bowman's capsule and the proximal convoluted tubule, down across the medulla, deep into the kidney, in a region called the descending limb of the loop of the nephron. We're going to have a hairpin turn. That now is going to round the bend and form the ascending limb of the loop of the nephron, and that's going to then lead into this final region, the distal convoluted tubule, and it too is going to be back into the cortex. So when you sum all of this together, we're going to find that Bowman's capsule and the proximal convoluted tubule are confined to that very narrow vernier, that rind at the edge of the kidney called the renal cortex. And then these multicellular structures extend as tubes down into the medulla. And we have one tube that's heading down deep into the medulla called the descending limb, and another tube then which rises up from the medulla back into the cortex called the ascending limb. And then these tubes then fuse with something known as the distal convoluted tubule, and we're back in the cortex. One of the ideas we're going to close with is the idea of an ion gradient, where we start out in the cortex at about 300 milliosmoles, and by the time we get deep in the medulla, we can be, in some cases, up to 1,200 milliosmoles. So we're going to see this tremendous gradient of ions and small molecules, particularly urea, from the cortex into the medulla. And we'll talk about how we'll use that to basically clean up and control the osmotic concentrations in blood. So let's start here, though. Let me start with a figure. This is a pretty picture, but I think it's worth spending a moment with it because it does a far better job than I did yesterday of describing the structure and organization of the renal corpuscle. Remember, we said the renal corpuscle contained the glomerular capillary, sort of surrounded by Bowman's capsule. And I think this is a much better image than that crude two-dimensional image I had on the board. So let's follow it through. This is the afferent arteriole. Blood is going to feed into this tuft of capillaries here called the glomerulus by allowing the blood to move through the afferent arteriole and then emptying into this group of capillaries, and we're going to drain the group of capillaries here out through the efferent arteriole. This is going to be one continuous pathway. It gets a little tortuous down here with all these folds in the glomerular capillary, but it's one continuous pathway. Then this continuous pathway of tubes, which we call the glomerulus, is surrounded by this epithelial structure here. This onion-like structure is meant to represent Bowman's capsule. And we have a cutaway view here of Bowman's capsule looking at the blood vessels contained within Bowman's capsule. But these are separate compartments. And where we're going to go now is we're going to talk about the endothelial cells lining the capillary and the epithelial cells lining Bowman's capsule here. And we're going to try to describe how we're going to move fluid from this compartment into this compartment. And how, in so doing, then we're going to move mostly sodium and chloride and water and glucose and amino acids from the blood vascular compartment into this cup. So that's where we're going to go now. But let's simplify the drawing here so we can follow where we are. So this sort of cup-like structure is meant to represent Bowman's capsule. And nestled within that cup-like structure, I'm going to show this as a single sort of oxbow in the blood vessel. But this oxbow is meant to represent the so-called glomerular capillary. The blood flow through this system is in this direction where the blood is being carried in by the afferent arteriole. And the blood then is flowing out into this tube from the glomerular capillary into the efferent arteriole. Well, I'm going to blow this up a little bit over here so we can see a little more what's going on at the level of these individual endothelial cells. So what I'm trying to describe here is the oxbow in the glomerular capillary. So these are meant to be the endothelial cells of the glomerular capillary. And we said yesterday that they obey all of the same rules we've talked about with endothelium before. That is, there is a basal lamina. And then right on the other side of those epithelial cells, and I'll show you these in blue, are these cells which we named specifically yesterday as being podocytes. But these podocytes are simply a fancy term for epithelial cells. They're a specialized term for epithelial cells of Bowman's capsule. And if we were to bring this structure back here, we'd see that there's a continuous line of these epithelial cells forming Bowman's capsule and extending into this structure, which they'll extend out a little bit more, known as the proximal, convoluted tubule. But recognize that this is a continuous layer of epithelial cells. Where we left off yesterday was to describe the two major pressures. We said that there was a hydrostatic pressure forcing fluid from the capillary into Bowman's capsule. We called this pressure the so-called hydrostatic pressure. We gave it a number. We said it's about 55 millimeters of mercury. The origin of that pressure is all the way back. If we follow from the glomerular capillary here back to the aphoid arteriole, back to the renal artery, back to the descending aorta, we'll get our way all the way back to the aorta and the left side of the heart. So the pressure that's generated by the contraction of the left ventricular myocardium is felt all the way out here in these capillaries. And we still have about 55 millimeters of mercury of pressure, a mechanical pressure against the wall of the capillary. This is the very same pressure that we talked about when we generated lymph, when we talked about hemodynamics. So there was a mechanical pressure, a hydrostatic pressure, moving the fluid from inside this capillary tube to the outside. The same thing's happening here. But now, rather than simply forcing fluid out into the extracellular environment, we've placed a cup around the glomerular capillaries where we can now collect that fluid. But just as we saw before, even though we have a mechanical pressure here, outward, put that in red, even though we have this mechanical outward pressure of 55 millimeters of mercury, that the gaps between the adjacent endothelial cells are tiny. Let's do it this way. The gaps are small. They're so small that all they permit is molecules of molecular weight less than 1,000 to pass. So from that, you'll see that molecules like sodium and chloride and amino acids and glucose, these molecules, small molecular weight, are easily going to pass between these endothelial cells. But the gaps are not so large that they permit the movement of molecules back here in the blood. An important component of the blood, remember, is plasma. And something like 8% of plasma is protein. The protein here in plasma has a molecular weight of about 40,000. So we have these big protein molecules. They're much too large to move through the tiny sieve holes that are the spaces between the endothelial cells. So we leave the protein behind, but we squeeze the water out. If we're squeezing the water out, that means we have water on this side. But because we squeeze the water out, we have more water on this side than this side. That now provides for another pressure. This is said to be an osmotic pressure. Just as in the systemic capillaries, we had an osmotic pressure drawing the fluid back into the capillaries, we have the same thing here. But now we can quantify this pressure. We can say that this osmotic pressure moving the blood back into the blood vascular compartment is in the neighborhood of about 30 millimeters of mercury. Well, there's one other pressure I want to put in purple. Well, let me draw this up here. So blue is the osmotic pressure, moving things back. This is about 30 millimeters of mercury. But now, if you can envision this mouth-like structure as a proper chalice or cup that's basically sealed off up here, then you can imagine how we can put fluid into this Bowman's capsule and begin to fill Bowman's capsule with water, with fluid. As we begin to fill Bowman's capsule with water, because this is sealed off, there'll actually be a mechanical pressure. We'll end up with a hydrostatic pressure. Put that in purple. We'll end up with a hydrostatic pressure of Bowman's capsule. So now as we've filled this balloon up with water, we have a hydrostatic pressure of Bowman's capsule. We can measure that. This is about 10 millimeters of mercury. So now if we add these up, we have the blue pressure of the hydrostatic pressure of the glomerulus as 55 millimeters of mercury. But moving in the opposite direction is the 15 millimeters of mercury of the hydrostatic pressure of Bowman's capsule. And, oh, let me put this in red. I'm sorry. So this is 55 millimeters of mercury. 15. And then in blue, the osmotic pressure, the water pressure, is about 30 millimeters of mercury. But that's also moving from Bowman's capsule back into the blood vascular compartment. So we have one pressure moving, in this case left to right, that's 55, and another pressure, 15 plus 30 is 45, moving fluid from Bowman's capsule back into the blood vascular compartment. But if you subtract these two, 55 minus 45, you now have a net pressure of 10 millimeters of mercury. A 10 millimeter pressure of millimeters of mercury pressure net in this direction. So now we have a delta P. We have a pressure differential. We have a delta P of about 10 millimeters of mercury. We've seen over and over again, whether it was in the lung or whether it was in the cardiovascular system, if we have a differential in pressure, we get a flow. So we're now going to be moving fluid from the glomerular capillary into Bowman's capsule. Now, it's going to be true that for each one of these nephrons, the amount of fluid that's moving is tiny. But when you begin to think about 500,000 nephrons in each kidney, 1 million in the two kidneys, now, even though the flow in each one of these is small, when you add it all up together, you get a number like 125 milliliters per minute. This is said to be the glomerular filtration rate. So the glomerular filtration rate is 125 mils a minute. We're moving 125 mils of salt water from the glomerular capillary into Bowman's capsule. Again, if you think about that for a minute, if you would fill your bladder at that rate, you'd get mighty uncomfortable, mighty fast. So there must be something going on here where we can reabsorb much of what we've forced from the blood vascular compartment into the renal compartment. And that's where we're going to head now. We're going to begin reabsorbing much of this water and sodium. So any questions up to there? Yeah?
Where did the 15 come from?
Where did the 15 come from? So the 15 is the hydrostatic pressure of Bowman's capsule. So if you imagine this, and this is horribly done in two dimensions, but if you imagine this is a proper cup, and if you imagine the blood vessel is sealed within that cup, and now you have movement from the inside of the blood vessel, which is the marker, into the sealed cup, you're going to fill that cup with fluid. Now it's true there's a drain out here into the proximal convoluted tubule, but you will actually fill this up with fluid. It's that fluid, the pressure accumulating, the fluid accumulating in Bowman's capsule that generates a mechanical or hydrostatic pressure, moving fluid from Bowman's capsule back into the blood vascular compartment. That can be measurable as 10 millimeters of mercury. 15 millimeters of mercury, yeah. Giving you a net outward of 10. Yes?
So the arrow that says 10 millimeters of mercury, is that the same as 15?
Oh, okay, so let's go through this again. There's 55, which is the mechanical pressure outward. There's 30 bringing things back in, that's osmotic. And 15 then is the hydrostatic pressure in Bowman's capsule. You add these two together, that brings us to 45. It's a net pressure moving fluid from Bowman's capsule back into the capillary of 45 millimeters of mercury. But that's 10 millimeters of mercury less than the hydrostatic pressure that's the force against the wall. So when you add it all together, there's a net pressure moving fluid from the capillary into Bowman's capsule. Because we have a pressure differential, a delta P, knowing we have Ohm's law, delta P is equal to the resistance times the flow. Now we're going to get movement of fluid from the capillary into Bowman's capsule. In fact, lots of it, 125 mils a minute in aggregate. Okay? Anything else? Yes?
So I'm sure I'm going to step on the wrong feet here, but so this is over the ejection stroke, though, right? So you have 55 on your heart.
Okay, so
There's an inverse when you're in relaxation, isovolumetric relaxation, where that pressure is going to push back on.
Okay, so let's be careful of this. Now, and I won't throw the slide up again, but if you go back to the slide that showed the pressure oscillations and you followed it out from the aorta into the arteries all the way down into the, by the time you start getting out into the smaller arterioles and you start getting out, particularly out here in the capillaries, you've lost the pulsatile nature of that pressure. It becomes a steady pressure.
Pretty constant. Okay.
Yeah, it's a pretty steady, constant pressure. And that's the 55 millimeters of mercury out here. Anything else? So now we've moved fluid from this compartment into this compartment. Now what I want to do in the upper panel, do this up in the upper panel, I want to lay out the epithelial cells. This is the epithelium. The epithelium of the proximal convoluted tubule. So I'm going to lay this out simply as a series of these ovals. That's meant to be the epithelium. This is meant to be the lumen of the proximal convoluted tubule. And then we have our typical orientation where this is the basal lamina. Now if we go back to this upper panel, sort of the lowest magnification view, the most zoomed out, and we follow this tube, we find this efferent arteriole extends around Bowman's capsule on the outside and then begins to snake around the proximal convoluted tubule. And as the extension of this efferent arteriole begins to wind its way around the proximal convoluted tubule, this now loses its characteristics of an arteriole and now becomes a peritubular capillary. Where the efferent arteriole had the characteristics of a typical arteriole where it was surrounded by smooth muscle, we're now back into the arrangement of a single layer of endothelial cells. It's a proper capillary. So now we're going to feed blood from the afferent arteriole to the glomerulus to the efferent arteriole, and now snaking around in a blood vessel called the peritubular capillary around the proximal convoluted tubule. Now let's go back here and simplify that a little bit. And rather than getting the complication of snaking the endothelium around the proximal convoluted tubule, let's just make it simple and make the two in line with one another. So this is intended to be the endothelium. This is the endothelium of the P-E-R-I, tubular capillary. So now we have in this tube, we have the fluid that we've pushed out of the capillary. So we're going to have water in here. We're going to have sodium ions, have chloride ions. We're going to have glucose. And we're going to have amino acids. Pretty much anything that was in the blood that has a molecular weight less than 1,000 is going to be out here in the peritubular capillary, because remember, this is the drain from Bowman's capsule. So we're going to have all this stuff out here in the peritubular capillary, and our next goal, what we're going to try to do, is to move this water, ions, glucose, and amino acids from this compartment back into this compartment. This is going to be reabsorption. So we can say that reabsorption moves water and sodium and glucose and amino acids back into the peritubular capillary. So how are we going to do that? Well, we're going to follow this again. Let me blow this up a little more and give you a little more detail. What I'm going to do is I'm going to take these epithelial cells and make them bigger and give you a little bit more three-dimensional image of that. When we look at these epithelial cells, they actually look a little bit like a cross. And I draw them, these are exaggerated, but I think it's worth thinking about it in this way. Because right at these short arms of the cross, we'll find that the cells are more or less plastered together by tight junctions. Now, up to now, we've emphasized the idea that we could zip adjacent cells together by tight junctions and make an impervious pathway between the cells. It's probably not quite that simple. And when we begin to think of these tight junctions here, I begin to think of them more as these kind of labyrinthine. I think there's an I in here, a labyrinthine pathway. Don't spell Greek words in front of an audience. Labyrinthine pathway between epithelial cells. So we're now going to see that down here in this narrow gap between adjacent epithelial cells, oh, I need to orient you. This is the basilar side. This is the lumen. And now what we're going to do on the basilar side, where these sort of short arms of the cross meet, we're now going to use a sodium potassium pump. And we're going to put a bunch of sodium out into this extracellular environment. And there will be a counterion with that, with the chloride. So now we have this high concentration of sodium chloride right here. And we have this short pathway between the cells, so that now we've generated an osmotic gradient so that water can move and snake its way between the cells down the concentration gradient. So basically, water moves around the epithelial cells in what is known as a paracellular pathway. In other words, we're using the local sodium chloride concentration here to draw the water. But in the process of drawing the water, because this is a sodium chloride solution, we now will bring sodium ions and chloride ions along with the water in the same route, and this is called solvent drag. Most of the movement of sodium and chloride and water from the proximal convoluted tubule back out into the extracellular space, most of that movement occurs between the cells in the so-called cellular route. So now we're moving the bulk of the sodium and the chloride and the water around the cells. But remember, we also said that we had these other major characters we had to get from the lumen of the tube to the outside world. These are the amino acids and the glucose. Now, the amino acids and the glucose, these guys, are going to be transported through a transcellular route or pathway. To do that, I'm going to come back over here and again reorient you, basilar, apical. On the apical side of these membranes, on this particular cell, I'm going to put a transmembrane protein. I'm going to label this as the sodium-driven glucose transporter. The way the sodium-driven co-transporter works is that out here in the lumen of the tube, we have a high concentration of sodium. Remember, we have pretty much the same concentration of sodium in here as we had in the blood. We've squeezed the sodium out of the glomerular capillary and into Bowman's capsule. So we have something in the neighborhood of about 130 millimolar sodium. Typically, anytime you look at the cytoplasm of a cell, the concentration of sodium inside the cytoplasm is about 10 millimolar sodium. So now we have 13 or 14 times as much sodium on the outside as on the inside. So you have a pretty good gradient. And what we're going to do is we're going to use that gradient in such a way that these sodium-driven co-transporters will, in the lumen, bind an ion of sodium and simultaneously bind a molecule of glucose. On the luminal side now, we bind a molecule of glucose, a molecule of sodium. This molecule, this transporter, effectively turns kind of inside out. And what it does then is it deposits an ion of sodium on the inside, and it deposits a molecule of glucose in the cytoplasm. So now we've moved the glucose from the luminal side into the cell. Then on this basolateral side of the cell over here, there's now going to be another transmembrane protein. I'm going to put this in red. And this is a facilitated glucose transporter. Now, the facilitated glucose transporter, which I need to name, and I didn't in the first section, is called GLUT2. The facilitated glucose transporter is this basically a gigantic transmembrane protein which allows for glucose to pass right through down its concentration gradient. So as we begin to accumulate glucose in the cytoplasm here, we now will get a gradient. Now, note where we are. We're across this basolateral epithelium. So now glucose is going to move from the lumen of the tube across the apical membrane by the sodium-driven cotransporter, find itself in the cytoplasm. And as those concentrations then increase, the facilitated glucose transport on the basolateral side allows it to literally pour out. It pours out into the extracellular space. Now remember what we have up here. This is blood. This is blood that if we walked back upstream, we would be back in the glomerular capillary. So this is blood from which we have squeezed out the glucose. So now what we're doing is we're allowing the glucose to move in this so-called transcellular route. This transcellular route is moving glucose across the basolateral epithelium out into the extracellular space, and then this can be picked up by the blood and swept away, keeping the concentrations of glucose in the extracellular space low, because as fast as we put it out here, it's swept away. We can walk through this in a similar fashion. I'll put a brown protein out here on the apical surface. This is meant to be a sodium-driven amino acid transporter. If you get down into the details of this, you'll find there are a variety of different amino acid transporters, some of them for charged amino acids, some of them for aromatic amino acids, some for uncharged amino acids. But all I just want to think about is this amino acid transporter. They all work on the same fundamental principle, and that is that they can bind out here in the lumen an ion of sodium. And simultaneously, they can bind out here in the lumen amino acids. So then when this turns inside out, we deposit the sodium into the cytoplasm along with the amino acid. And again, on the basolateral surface out here, there's going to be a facilitated amino acid transporter. So that those amino acids which have entered the cytoplasm can now diffuse through this channel out into the extracellular space. And they, like glucose, can move from the extracellular space back into the blood vascular compartment in the peritubular capillary and be swept away in the bloodstream. So in this way now, we are reclaiming sodium, and we're creating sodium and amino acids and glucose through these epithelial cells, these epithelial cells of the the epithelial cells of the proximal convoluted tubule. But at the same time we have this transcellular transport, we have the paracellular transport of water and sodium moving between the cells. And in this region of the proximal convoluted tubule, we are reclaiming something like 60% of the sodium and 60% of the water and 100% of the glucose and 100% of the amino acids. Let's take this now and try to put this in context. I'm going to put this in the backboard. And we did this yesterday, but I think it's worth laying this out again. So this is meant to be the structure of the kidney. We divided the structure of the kidney into the region called the renal cortex. The renal cortex is its outer rind. So this is meant to be the renal cortex. What we've talked about so far today is we have talked about Bowman's capsule and the proximal convoluted tubule. And those are all confined to the renal cortex. But once we get inside the tube of the proximal convoluted tubule, and we follow that out, we now then follow it down in this direction. It takes a turn, comes down deep in the medulla, because remember, this whole section in here, this is meant to be the renal medulla. And if we follow this tube of epithelial cells, it begins up here in Bowman's capsule, extends into the proximal convoluted tubule, but then extends into this structure known as the descending limb of the loop of the nephron. Down deep in the medulla here, there's a hairpin turn. This tube takes a turn. We label this as the hairpin turn. The tube then continues. In this structure, I'm going to label the ascending limb. Of the loop of the nephron. The ascending loop of the nephron then empties here into the distal convoluted tubule. Now recognize what we've drawn here and how that is equivalent to the list we put on that right-hand panel. We said that Bowman's capsule and the proximal convoluted tubule are in the cortex. The descending and ascending limbs, along with the hairpin turn, are located in the medulla. But because the tube makes a U-turn, it feeds into a portion of the tube up here called the distal convoluted tubule. That's all nephron. Then that structure, these nephrons, are now going to empty into another structure here, which we described yesterday as the collecting duct. Now I've drawn this as to show one nephron emptying into one collecting duct. There are probably more like 20, 30, 40 of these nephrons emptying into collecting duct. But they all empty into the collecting duct in the cortex. And then this tube then extends across the medulla and empties into the region down here known as the renal calyx. Now, the last piece here, I want to point out a couple of things. When we look at ion concentrations up here in the cortex, we find that the concentrations are in the neighborhood of about 300 milliosmoles. Now, of this, about 130 is sodium, about 130 is chloride. We have about 5 or so of potassium, some glucose, some amino acids, and some urea. When you total it all up, you find that the total osmotic strength out here is about 300 milliosmoles. But if we look at what is known as the cortical medullary gradient, we find that the concentration of ions and small molecules, mostly urea down here, deep in the medulla, can be in the neighborhood of 1,200 milliosmoles. Now, those are numbers, but just recognize that there are almost 4 times as many ions and small molecules down here deep in the medulla as there are up here in the cortex. And this generates a corticomedullary gradient, so that as we dive deeper and deeper into the medulla, the concentration of ions and small molecules gets higher and higher and higher. And what we'll see tomorrow is it's the epithelial cells here of the descending and ascending limbs of the loop of the nephron that generate this corticomedullary gradient. And then finally, we'll use that corticomedullary gradient to do the final the final concentration of urine as the fluid descends through the collecting duct, and we'll talk about that tomorrow.